Let's define the curl of a vector field. Just like divergence, the curl uses the nabla operator, and so we define curl to be nabla cross f. That is the vector of partial derivatives cross the coordinate vector function, which represents the vector field. So we have m, n, and p. And so now, just like we have done many times in this course, we compute the standard cross product using the subscript notation, which we've used from the very beginning of the course. So first we do 2, 3. So we do the y partial of p here, and then we do minus 3, 2. So we do the z partial of n right here. And then 3, 1, we do the z partial of m here, minus the x partial of p right here. And then lastly, we do the x partial of n here, minus the y partial of m here. Now, you can memorize this, or you can just compute it with the subscripts each time. It's really not that difficult, but I will make a point here. When you're looking at a vector field with only two coordinate functions, you're going to only be interested in this particular coordinate. And this we will see a lot of when we study Green's theorem. Now, when the curl is identically the zero vector, we define f to be conservative. So that's what we want to show with a particular vector field that we have here. And then what we want to do is compute the potential function. So now we have the vector field zy to the minus 1, first coordinate function, then the second coordinate function negative xz y to the negative 2, and then for the third coordinate function, which is p, we have xy to the negative 1 minus 1. Now in order to do this, we can just go ahead and follow the formula that we've written. So we do the y partial of p. By the power rule, that'll give us a negative xy to the negative 2, which we have here. And then we do the z partial of n, and that'll give us a negative y to the negative 2 times x, minus minus gives us the plus xy to the negative 2. Now for the second coordinate, we need the z partial of m, which will be y to the negative 1 here. And then for the next term, we have the x partial of p, which gives us y to the negative 1 subtracted that we have here. And now for the last coordinate, we do the x partial of n. That'll just give us a negative zy to the negative 2 right here. And then we do the y partial of m, again by the power rule, that'll be negative zy to the negative 2, minus minus gives us the plus zy to the negative 2. And you note here that each of these coordinates result in the zero coordinate. So by definition, we do have a conservative vector field. Now, what that means, the equivalent condition, is that there is a potential function whose gradient is f. And so we just maximize our use of notation here. So that will mean that the x partial of the potential function will be m. That is the first coordinate function here. And so we just do partial integration with respect to x. So now, of course, these are constant relative to x. So we get xzy to the negative 1. And then, of course, we can add a constant that contains the other variables y and z. Next, the y partial of the potential function will be equal to the second coordinate, that is negative xzy to the negative 2. And then we do partial integration with respect to y. So again, add 1, divide by the new power. The new power is negative 1. We divide by negative 1. We absorb the negative, and we get xzy to the negative 1 plus a constant in terms of x and z. And then we take the z partial of f, which will be equal to the third coordinate, xy to the negative 1 minus 1. Then we do partial integration with respect to z. Okay, this is constant relative to z, so we get xy to the negative 1z, And of course here we just get a negative z, very simple integrals, and then a constant which can be a function of x and y. Now in order to find the potential function, we just compare the equations for f. And so we see that we have this equation, or this term in each of the equations, so we need that, the xz divided by y, and we also need the negative z. Now again, at this point, all of these terms will provide us the vector field upon partial differentiation. And so we should add a constant here, c, to make this the most general form for the potential function. So our potential function will be xz divided by y minus z plus an arbitrary constant. And we are done.